Hello everyone. Today we are going to talk about regression slide. Um, this is the highlight of the statistic course we have been learning so far this semester. We're gonna basically incorporate everything we have learned and why this regression is so important and how we derive each of these definitions in detail. So the idea of regression is, in previous section, we talk about the association between A and B, right? Um, so if I want to know the association between X and Y, we are able to calculate covariance or correlation in previous chapter. But it doesn't mean that the association doesn't mean that it gives you the direction, but it doesn't tell you necessarily how much increase in X affects like your Y. For example, if you are interested in in previous chapter we studied the temperature and GDP association of that, right? But in regression part, we're gonna deal with, okay, if temperature increase by 1 Celsius or 1 Fahrenheit, and how that affects our GDP. What is the expected impact of a change in X and Y? That those are the things we're gonna discuss in here, and that is actually one of the benefit of using regression analysis. So we will apply estimation. We learned in, I think, chapter 8, hypothesis testing. We learned in chapter 9 and 10 to this regression model. So the relevant chapter is chapter 16 of your textbook. So many of you guys probably took, introduction of the economics, right? Econ 110 or 111, like that, right? So do you remember what was the marginal cost and fixed cost? So let me test your knowledge. So let's make assumption that marginal cost is 2, fixed cost is 10. So which is a wrong statement? By the way, what is the marginal cost and what is a fixed cost? So can you tell me? I mean, since I'm recording, so you guys basically cannot tell me, but try to think about that. What is the marginal cost and fixed cost? The idea was fixed cost doesn't change no matter how many products you're producing, right? But marginal cost is like, okay, how, every unit you are increasing, that is additional cost uh, that you're gonna need to pay. So basically the number of products you are making is matter. It doesn't matter for this marginal cost, but not for fixed cost. So for example, when you produce 5, what is the total cost? Total cost is a fixed cost plus marginal cost time to produce the production you're making. So 2 times 5 plus 10 is 20. So when you produce one more, the total cost increases by 2. Actually, that is a definition of marginal cost. So every 1 unit you are increasing, your total cost increases by 2. Remember, this is a very, very important concept. So this is actually one of the interpretation you're gonna have in the following slides. I'm gonna explain in detail, but also relevant for your if you want to interpret the coefficient, then this is how it's going. So I'm going to cover this in more detail. So when you produce 10, what is the total cost? For example, it's 10 times 20, which is 20 plus 10 is 30. Average cost is total cost divided by total units. So 30 over 10 equal 3. So that is also correct. So if your budget is 40, how many can you product? So you subtract it from, so 40 minus 10 is 30 because fixed costs you got to subtract. So the remaining cost is 30. So you basically divide by 2 so you can produce up to 15. So answer is E, everything is correct. So econ 111 or econ 300, you are able to find the optimal production given marginal and fixed costs, right? So basically those are your supply, right? Supply curve, the marginal cost equals supply curve in econ 111, right? The 110. So in econ 320, so we are actually trying to estimate that. So The production and total costs are observed, and marginal cost and fixed costs we don't know. So what we know is how much they are producing, and then the total cost. We have no idea what is the marginal cost or fixed cost. So this is actually data-driven analysis. Given the data we have, we want to analyze and we estimate what is the marginal cost and fixed cost. That is actually highlight of Econ 320. So you learned the theory in the previous courses. Now you are applying your theory to estimate the true parameter. Because in previous courses, they are teaching you what is total cost and then marginal cost, but they never ask you to find actual total cost or marginal cost from data. This is the thing, we're gonna do that. So we don't know marginal and fixed cost. Still, we want to answer this question. So when you produce 5, what is total cost? When you produce 1 more, what is the additional cost? So how much the total cost increase? So that is additional cost. In other words, that is the definition of marginal cost. What the loss if you produce none? So that is basically fixed cost because you are producing nothing. Your loss equal basically fixed cost. To make average cost equal 3, how many you should produce? If a buzz is 40, what is the amount you are producing? So let's say this is January, some months and then output and cost. These are our data set we are having. So let's say this is, if we plot them, this is gonna be looking like, this is like a scatter plot, right? I ask you guys to basically draw the scatter plot, right? If you are looking at the assignment or project I posted, so basically these are each observation, you're gonna see that. But so what you can see is, oh, they have a positive association, right? So that was the first idea, and we want to estimate what is the marginal cost and fixed cost. So let's come back to the basic ideas. What is the marginal cost and fixed cost? If you are going back to the algebra, what is that meaning? So basically, the fixed cost is like intercept, right? Because it's fixed. So when x equals 0, when output is 0, right? And what is the corresponding the value or y-intercept? Basically, fixed cost equal intercept because that is definition of that. When you don't produce anything, what is your total cost? Or in other words, that is your fixed cost when you don't produce anything. So imagine you're drawing some line, something like that. Try to fit this one, something like that, right? So imagine this is a line. Can I change the color? Oops, oh, no. Okay. But anyhow, this is basically the line I'm trying to get from algebra, right? So based on data, I'm trying to fit as nice as possible. That is actually ideal for the regression. So given the scatter plot we have, we want to find the association between these two. So we are trying to actually fit the data very well so that we can estimate the slope and the intercept. That is actually regression. In something easier way, say. So the intercept you are getting is a fixed cost in this data sets. So this is like this. So basically in algebra, we know y equal mx plus b, something like that, right? In algebra 1 in high school 10th grade. So in other words, the intercept is b and slope is m, right? So basically the slope is telling you, so interpretation I'm gonna cover in detail, but for this example, the m is a marginal cost, and then the intercept here is basically a fixed cost. So m is basically slope, right? Your slope, or it's marginal cost in this example. B is intercept, or in your example, fixed cost. Think about the idea of fixed cost. That is, you produce nothing. What is the total cost? That is basically fixed cost. Slope, what is slope? Basically, it's a rise over run, right? So when you are selecting 2 points, for example, number 3 and 4, for example, then when x is increased by unit, how much y increase? That is actually basically the slope. Yep, so that was the idea. So when x increased by 1 unit, how much y increase? That is the slope, rise over run, right? Or change in y over change in x. In other words, when x change something, how much y change? That is the slope. In this case, x increased by 1, how much y increase, or the change in y over change in x, that is the slope, or our definition of marginal cost. When x increased by 1 unit, how much the total cost increase, that was marginal cost. So, I mean, those who are taking some advanced calculus course, you might think this has a differentiate total cost with respect to the additional output. That is actually slope, but yeah, you don't have to know that for this course, just for your information. So that was the idea. So this one was intercept. So your fixed cost, and this is your marginal cost. So okay, let's move to the next section. So in our regression model, this is exactly the same thing. Previously, what I had was this one, right? I'm gonna just bring, can I bring this to? No, probably not. Okay. I cannot bring. Okay, it doesn't matter. Okay, so this is a yi equal beta 0 plus beta 1 plus x. This is very standard to form your linear regression model. So keep that in mind. In previous case, what I actually wrote was something like that. Y equal mx plus b, right? That is m is slope and b is this. So if I reorder this such that it's going to be y equal beta beta plus mx, you know. So basically these are the same. So here beta, this b was intercept, same in here. This is your intercept, you know. So that's why it said it's a fixed cost as I described before. So the m here was slope in our previous example, right? But now it's a beta one. So beta one was marginal cost as I explained just a minute ago. So that was the idea. So what's the difference between this one and this one? So you notice that you see something, right? This is actually error term. Why do we have an error term? Let's come back here. So for example, oops, okay. I drew this line. The error term is coming from here. I mean, this is something I'm trying to fit this line, but as you can see, there are some differences over here, and there are some differences over here. There are some differences over here. The difference between this actual data, this is actual data, but this is something you are trying to predict, you know, or fit the line. The difference is actually residual or error term. So this difference is error term. So this regression model is yi equal beta 0 plus beta 1 xi plus epsilon I. So this is usually error term, unknown, random. This beta 1, beta 0 unknown, but constant, and these are observed. So basically, these were our original data, and this one is like your y's. So this one is your x's. So each of this pair is like your observation. For example, this one is for your x, x1 comma y1, and the second one is basically x2 comma y2, and then dot 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 dot. It's gonna be just yn comma x xn comma yn, something like that. So each of these observation is something like that. So if we plot this pair, this is like it's like a coordinates, you guys learn in high school. So if you plot that, it becomes scatter plot. If we try to fit the line using some kinds of model like algebraic model, then this could be your answer. Algebra model. So that was some backgrounds. So basically, our goal is given this data set x and y or total cost and then output. We are trying to estimate, trying to guess our true parameter using this data set we are having. So beta 0 and beta 1 are actually we are trying to estimate. This is a simple regression model. So in your project, I ask you to find the effect of something on something, right? So, but what if we have more than one variable? Since in this case, basically you are looking for the relationship between output and then your total cost. So if x increase by 1 unit, how much y increases your model? But if we extend this to the multiple regression model, this is actually simple regression model that you only have one x. You can simply extend this to y equal beta 0 plus beta 1, x1, x1, and then plus beta 2, x2, plus beta 3, x3, and then some epsilon I, something like that. So why do we put the I? That I indicates your observation. For example, here I equals January, I equals June, July, I equal December, like that. So those are basically this one indicating, subscript indicating which month it is coming from. So, or it can indicate observation 1, observation 2, observation 3, etc., etc. So, another example. So I mean that was basically ideal. I mean previously this was a multiple regression model. This interpretation would be, I'm going to explain in detail, but for your information, the interpretation of this one, simple regression, is when x increase by 1 unit, how much y change. For example, if this beta was 2, and I mean, it depends on your context, So answer is, if x increasing by 1 unit, how much y change? But here it's positive sign in front of x, so it actually increase. But if it's negative, then it decrease. So your interpretation would be, if x increasing by 1 unit and y increase by 2. But our unit is what here? So let me write down here. So interpretation in simple regression is interpretation. Well, simple linear model is like when x changes or x increases by 1 unit, y changes by beta 1 unit. So that is your interpretation of this simple linear model. So here, just keep that in mind, that the unit change depending on your question. For example, if you are looking for this one, so if this beta 1 is 2, so then your interpretation would be something like that. Okay, so okay, when output increases by 1 unit, so basically this is output is like a unit, or if you produce 1 more, something like that. It doesn't have to be ending with a unit. For example, previous case I said that if when, or in our previous lecture we said when temperature increases by 1 unit or something like that. So that was previous, example we did the last chapter. But in this specific case, when output increased by 1 unit and the y was what? Y was what? Your cost, right? So your the total cost, total cost, it was positive, so it increases by 2, maybe $2 if this is dollar, something like that. So that is your interpretation for this one. So you can apply this interpretation for your project, so when you are doing simple linear case. But let's say if I'm interested in actually this model, multiple regression model, which most of you guys gonna choose, because I ask you to choose more than 3, so you might need to choose something like a P4, X4, something like that. So, and your interpretation would be basically, okay, everything is the same, but you need to put, for example, interpretation, you need to interpret separately. For X1, for example, interpretation of X1 is, okay, holding other things constant. So constant. So basically, because why you're saying holding other things constant? Because you are basically conditioning on x2 equals something, x3 equals something, x4 is holding constant. You want to analyze this. That is actually a benefit of using multiple regression. So you can say, I said holding other things constant. You can say another way, holding x2, x3, and x4 constant, when you can do the exactly same thing. When x increases by 1 unit, y changes by b1 unit, something like that. For example, in your project, you can say, okay, for example, when the student to faculty ratio, so I mean, let's say holding the admission rate, and then, whatever thing, a full-time students ratio holding constant when students to faculty ratio increase by 1 unit, then your graduation rate will something like a decrease by 2%. So every one ratio increase by 1, then your graduation rate. So basically, why should it be changed based on your context? In here, it does total cost. In our project, it's basically a graduate rate. So it should be percentage. So your graduation rate changed by whatever percentage, not units. For example, if a coefficient of this one was something like, okay, -3, and this was something I just made up, -2, +5, and this was plus 0.1. So that means, okay, holding x2, x3, x4 constant when x increased by 1 unit, the something like a graduation rate increases by 0.1 percentage. That is your interpretation. Something like that. This is okay, x3, for example, is a holding x1, x2, x4 constant when x3 increased by 1 unit, the graduation rate decreased by 2%. Those are basically highlights of this. So honestly, you know what, I'm just giving you the all answer for your project. So and I even gave you the code. So as long as you follow this lecture and just finish your the project, you are in good shape. But try to interpret as detailed as possible. Also keep in mind that not only you interpret like that, tell me whether that relationship makes sense. Discuss as detailed as possible, okay? Oops, can I? So more examples in economics. So this is demand supply function. I mean, this is quantity and price. So you can estimate beta 1 and beta 0. So take a look at that Keynesian consumption. For example, your income increased by 1,000. If this is 0.7, 70% of income goes to the consumption. This is actually very, very famous. This function, but these are the example. Not only you can estimate marginal costs and fixed costs, you can apply this regression analysis for your demand, and then this kind of thing. For example, this is quantity and price. So if beta 1 is like something like a -1, something like that, and price. So basically, you can draw something like that. This is your quantity, oh, this is lag, okay. This is quantity and price, okay. And then since it's -1 and intercept is like say 5, then you start from 5 and slope -1. This is your demand curve. Basically, this is how it's working. But you're gonna have some error term, residual term, because you're gonna have because the data doesn't have to be fit perfectly on the function. We try to best to fit that. So these are terminology we're gonna use from now on. So y is your dependent variable. So and then x is your independent variable. So they says it's dependent. It's sometimes it's called a response variable, or it's like okay, response variable. Sometimes people call that, but most of the time we're gonna call this dependent variable. X would be independent variable. Sometimes people say explanatory variable, but either way it would be fine. Beta 0 is intercept, constant term. Beta 1 is slope, as I discussed in detail, so etc. etc. So again, when you have more than one x, it's gonna be multiple regression, which you're gonna use for your project. This was our idea. This was slope and error. I already explained. So I already explained that. And actually, we are estimating this beta 1 and beta 0 using this data. And we're gonna estimate this using a least square estimation method. In other words, I mean, I was keep saying that we are trying to fit as best as possible. That is actually least square estimation method. We call OLS. This is basically the model we're going to use from now on. This is a linear model, but idea is, I mean, based on this data set, we are trying to estimate beta 0 and beta 1, but by trying to fit the data set with this line as close as possible. Those were ideas. So, I mean, I explained in detail how you can use this thing for your project, you know, I mean, the R program. But as I promised, and I explained in detail for this chapter, so you can actually use our Excel, but I recommend you to use R program for your own learning. But details of explanation, I went through here, but I'm not going to explain more. And once you're gonna learn regression in Excel, these are the output, interpretation to be same. So next to the intercept to be 8.1, this one, and this is your x-intercept. So for example, you can write this model again as something like this. Okay, let's think about this as, okay, y, whatever y you're having, equal intercept is 8.189. and it's positive, so it's a 2.383 times just x1. So these are, and then plus residual, so something EI, and put the I if you like. So maybe I over here. Okay, maybe here, something like that. But these are the basically linear regression forms. And see, we're gonna have a t-test of this one. And we have a p-values and 95% confidence interval. And these are F statistics and R square. Actually, everything here will be used for your project. So I'm gonna explain here. So interpretation of this one would be when X increasing by 1 unit, Y change by 2.383. But I don't know, it depends on your context. When X is something temperature, you say when temperature increase by 1 unit, Y, whatever thing, GDP increase by 2.3, something like that, depending on the context. If this is like a marginal cost and a fixed cost, then this were your marginal cost was 2.383, 8.189 is actually your fixed cost. So this one was by definition of algebra. This one was basically your fixed cost or intercept, right? So when X equals 0, what would be the variable Y? That is actually your intercept. Or when you are having cost information, when you don't produce anything, the expected whatever intercept would be your fixed cost, because that is definition of fixed cost. No matter how much you're producing, you're still paying it. So when you produce nothing, the amount you're paying is a fixed cost. So based on standard deviation of coefficient, you're able to get t-stat. So you remember t-stat? We learned t-stat in previous cases. I went over many times. T-stat was very similar to z-score. Pretty much the idea is exactly the same. So we are saying t equal basically whatever thing we are having. For example, I'm gonna just have this one is 2.383. And then subtract 0 over, so something like that. This one over, so like your standard of error. So our standard of error previous was sigma over square root of n, right? Or this one was basically, this one was like your x bar minus your mu and over your sigma over sigma over like a square root of n, something like that, right? And it was sample size. I mean, this one, sorry, I tried to type it, but this is best I can. But this was basically the idea was sigma over square root of n was your standard of error, and this one, it looks like a z-score. Basically, this was z-score, method of z-score. Or G and T are basically similar, but when the sample size is low, like a 12, or then we tend to use this T distribution, but idea is pretty much very similar. So, I mean, the nice thing is you don't have to calculate those t-stat or standard error by hand, as program will give you, So in the project, I didn't ask you to calculate t-stat, but I asked you to interpret the t-stat, right? So based on t-stat, if you come back to chapter 9 or 8 and 7, you're able to actually calculate the p-value, right? And you are able to get the 95% of confidence interval, right? So basically those x bar, x bar was 2.383 and mu was population or the thing we are hypothesizing. For example, this is for your information and very important. Hypothesis value is always beta 1 equals 0. Or and then alternative would be just beta 1 equal not 0. It's not equal 0, something like that. So these are always your hypothesis. So remember in the previous cases, like when you find the t-stat and p-value, we need to have a hypothesis, but almost 100% time, at least this course, we're gonna make the you're estimating basically against this one. So your hypothesis is basically whether the coefficient beta 1 equals 0 or not. So same thing over here. Your intercept was beta 0, right? If you come back to this this thingy, this one was your intercept and this one was your beta 1. So your null hypothesis is always equal 0 thing. So you can switch this to 0, 0 and then 0, same thing. So that's why I'm subtracting 0 from 2.383. So I'm subtracting 0. If I'm hypothesizing this equal 3, for example, and not equal 3, then I should put this equal 3. But since in this regression part, we are gonna use only zeros. I'm gonna explain why we are using 0. Because this is testing you. So what if, this is 0? Then x, so if this is 0, this implies what? So x1 does not affect y. That is your interpretation. So your alternative hypothesis is, oh no, it does affect y. That is your alternative hypothesis. So you are testing whether x1 is affecting y or not. In other words, for your project, it's gonna be okay, whether student to faculty ratio affects graduation rate or not. So if you have a very significant result, like a p-value is very low, like less than some alpha, your threshold, it can be 5%, 1%, or 10%, then you can say, oh, we've reject the hypothesis at 10% level, or 5% level, or 1% level. So I'm gonna give you an example like this, okay? So imagine that, so these are our hypotheses. I'm gonna just write over here. So imagine that these are our examples. So graduation rate equal something that I'm just making up. So like 30% is intercept, and then 3, and then actually 2 times the fraction of full time. So fraction of full time, and then minus 1.2 and students and the faculty T ratio thing, something like that. Let's imagine, and then just put another thing, and then 0.2 times enrollment this rate or something like that. So interpretation of this can be actually for this one, holding student faculty ratio and enrollment constant when fraction of full time increase by 1 unit, and then this one graduation rate will increase by 2. Holding for this one, holding fraction of full time enrollment constant when student faculty ratio increase by 1 unit, then it's gonna graduation rate decrease by 1.2, etc. But that is not all. So what we want is to test it out. So let's given that, I'm just making a number that, let's say after you do the regression, I get p-value of fraction for equal 0.11. I'm just making a number. And then, okay, I'm gonna just write down everything. So p-value of students, faculty ratio, p-value of faculty ratio equal 0.011. And then enrollment, I'm on it again, of enrollment equal 0.0001, something like that. I'm just making the numbers. So how we interpret this, okay, since this is a significant or not, I mean, if we come back chapter 8 or 9, 10, I explain in detail how we get p-values and then how to interpret those, right? So since this is greater than our alpha, right? Alpha. So say alpha conventional thing, or I prefer to use 0.05 or 0.01. So this one is actually what? Higher than this. So you fail to reject. That means our hypothesis is always against the 0. So our null hypothesis was, okay, fraction of full time does not affect graduation rate. That was your null hypothesis. So this one, or in other words, or your is a fraction of fraction of full time, does not affect, but it does affect is why. Or you can replace it, students to faculty ratio does not affect your null hypothesis, and enrollment does not affect your null hypothesis. It's always in regression cases. So basically what you're doing is, okay, then this p-value is greater than 0.05, so you fail to reject. Your conclusion would be, oh, okay, fraction of full time actually does not affect. That is our conclusion. Cool. So it's not relevant. It's not really important. So when you recommend for your, the student officers, then, oh, okay, student to faculty ratio doesn't matter. But let's say the students of, no, actually fraction of full time doesn't matter. But let's say students to faculty ratio, this one is actually less than 0.05. So we reject the null hypothesis at 5% level. So it actually does affect. Students to faculty ratio does affect by negative 1.2 for graduation rate. So very, very important stuff. But we cannot reject at 10%, 1% level, because it's greater than 0.01. So you also need to discuss that. So lastly, this one is less than 0.1. So enrollment, we reject the null hypothesis that fraction, the enrollment doesn't matter. So it actually doesn't matter a lot, and we reject at 1% level. So very important. So beside of the interpretation, you also need to interpret those p-value, t-stats, etc. So given this t-stat, you can calculate the p-value. I just explained t-stat. T-stat is basically ratio of these two because this is always 0. So you are subtracting 0. So basically it's gonna be just something like that. So equals to basically beta 1 over standard of error, something like that. So 2.383 over 0.206 is 11.587. Similarly, 8.189 over this one is 6.985. So given this, they already calculated for you the 95% confidence interval. You don't even have to calculate that. So what is important in this regression is, okay, beside this interpretation, you need to interpret and show how important each of the regression. So pretty much I'm just giving you the answer, right? So this one has observations. I mean, in our program, you're gonna have very similar types. I actually, in the previous video, for the project video, I help you to find all the values in our program. I highly recommend you to use R. Those are free and absolutely good for your education. So the R square is also another very important thing. So R square is, those R is coming from correlation coefficient that we learned in previous chapter. So this R square is basically the R, we are looking for the correlation square. So correlation square is R square. The interpretation of this is, okay, how much of the variation can be explained by X? I explained in detail in previous video the project. So R square is also important. I mean, in the project, I ask you to try to interpret those. So F statistic is another important. So when you decide whether model is good or not, you interpret that. And corresponding p-value, significance F is this. Try to interpret this on your own, okay? So when this p-value is the same thing, it's the same as this p-value. It's less than something, alpha threshold, then you say it's significant or not. So basically it's less than 0.01, so this model is really good. So those are your interpretations. So I'm gonna move to the next part. So I think I pretty much explained almost everything you need for your project at this point, you know. So basically you have a p-value and standard error coefficient. First, interpret coefficient, discuss your leisure significance, discuss your null hypothesis as well, and what is the meaning of rejecting that, interpret in detail. And then for your final project, you're going to have more of this other than one variable. So discuss those as well. Discuss F statistic, R squares, and discuss overall finding, whether those coefficients make sense, signs make sense or not. So discuss in detail, okay? Okay. So this part we already explained in previous estimation chapter, like chapter 8. So if expected value of these are the basically same. I mean, OLS estimators are unbiased estimator. It's also consistent. So these are some properties that, okay, these are how you get the standard error of regression. So I'm not gonna just deal with this very much. This is how you get the standard deviation of beta 1. Take a look at this, but I will not explain super detail, but I will just ask you to focus on those interpretation more detail. But by all means, if you have any question while you are trying to come back here, just let me know. But this, as I said, this is our t-value, you know, null hypothesis is always beta 1 equals 0. Beta 2 equals 0, beta 0 equals 0. Something like that is always our cases. And as I discussed previously, this one is how you get the t, because this mu 0 equals 0 over here. So p-value we explained in previous chapters. So tell about I already explained those in detail. So those are, I just explained you as well. So comparing this to that. And this is another kinds of example, return to education. So Y is your wage and X is your education. So basically interpretation is when your education increased by 1 year, the unit is year. So those are very important. That's why even if you have the same regression, depending on the context, your interpretation would be totally different. So when X increased by 1 unit here is year, then how much Y increase? Y is what? Hourly wage. For example, if beta 1 is like, let's say 0.2, then when you have 1 year of more education, then your Y hourly wage increased by 0.2 bucks or 20 cents. So those kinds of things. So beta 1, which is slope capture return to education, beta 0 is expected wage when no education, when X equals 0. So it doesn't mean much. So you are able to actually do that, try do this, okay? So we actually went over this in detail in chapter 9 and 10. So this is just a repeated thing. So try to do this one as well, okay? These are actually very, very important for your final project. So take a look at, because it's basically saying that as I explained you, so I'm just skipping that part. So p-value thing as well. So sometimes you're gonna just test it out against beta 1 equal 0.7 or some other thing, because in our project, and most of the time you're not gonna use that. Most of the time you're gonna just test it against the 0. So that's why I don't focus on that. But only difference was previously was beta 1 minus 0, because those are the thing we are hypothesizing. But now replaced with 0.7 as we did in chapter 9 and 10. So nothing is different. It's basically the same. So basically same, exactly same thing. So nothing has changed. So residual is, I mean, something, these were the actual cost, but the residual was what? Based on our interpretation previously, I mean, the difference here would be your interpretation. For example, based on this algebra thing, for example, this one, let's say this is your answer. Like beta 0 is 8.2, beta 1 is 2.38. So your formula would be actually something like that, right? So y total cost equal 8.2 plus 2.38x, right? Plus residual. But you can write either this way or this way. So this was our model we previously explained. You can say y hat, like here, this is y hat, equal 8.2 plus 2.38 x. So only difference is you have a residual at the end, then you're gonna use y. But if you don't want to, I mean, and this is equivalent to this y hat equal 8.2 plus 2.38x. So you don't have a residual. So this is y hat means it's a predicted value. So for example, let's say you are looking for education level equals 6.5, then plug in the value. This is something you're predicting. So let's say you are plug in 6, and this is your predicted value. If we plug in 6, what would be the case? So your expected value is multiply 6. So do the calculation, math. So plug in, it might be something like a 22 point something, right? But your actual value is a 20, but your predicted value, y hat equal 22, let's say, for convenience. But the difference here is what? Like 2, right? Those are your residual. So the thing, but this, since this is below the predicted value, so it should be negative. So on the other hand, this is y hat minus y, or y minus y hat. Actually, the y here, this is y actual value, right? Y minus y hat would be your error term. So residual thing is y minus y hat. Just keep that in mind, okay? So for example, your y here is 20, but y hat equal 22. So your residual is actually negative 2. And sometimes you're gonna have positive, like over here, up there, but sometimes you're gonna here you're gonna have a positive residual, but on the below you have negative residual, etc. So I mean, those are basically the ideas. So this is predicted cost, the actual cost difference is residual. So y minus y hat. Those were the ideas, so residuals. So when you decide to take more advanced econometrics next semester or following years, you're gonna learn more about this one, but I'm not gonna explain very detailed. Okay, so the residual is basically unexplained part. So we are trying to explain this data as much as possible using this fitted line, right? So that's why this part is explained part, and this is unexplained part. So that those are the idea. We are trying to explain those why using this these two. So yeah. So basically using these 3 graphs, what you can see is, okay, this one has a lot of residual errors, less residual, 0 residual. So this one, the model we are having in blue, explain 100% of the data. This one may be 80%. This one may be 60%. The percentage actually, by the way, I'm talking about is R square. So basically R square is how much of the variation of Y can be explained by X. Those are R square. So this one, the variation of X explain Y 100%, 80%, 60%, something like that. Okay. So these are some of the theorem and basically the estimation method for least square. So idea is here. I'm not gonna go over the detail, but idea is when you have this data, I'm trying to fit a line as detailed, as close as possible, so that you can find the beta 1 slope and then intercept. So those are your method. So just take a look at, but I'm not gonna go in detail. So in our program or Excel, they're gonna do these steps for you. Just keep that in mind. These were basically the ideas, and these were marginal cost and fixed cost. Okay, okay. This is how you get the beta 1 and beta 0 by hand, but I'm not gonna go over this detail because this is a little bit more advanced. And I know if you're more interested, you can learn it in the advanced courses. But I'm happy to discuss this with you if you are seriously interested in more. I'm happy to talk with you. Okay, then I think I pretty much explained everything. Those are something I explained in previous chapters as well. Something I want to discuss. These are just more examples. I went over pretty much everything, but different examples. Something I want to discuss more is basically this R square thing, but I already explained you this thing, but R square is here. It's between 0 and 1. Measure the strength of the relationship between X and Y. As R square is higher, close to 1, I previously say 80%, 60%. 80% means 0.8, 60% means 0.6, something like that. It's between 0 and 1. Just take a look at that. That is, oh, this is actually interpretation of your, for your project. So just keep that in mind. So these are multiple regression. I actually explained in very, very detail previously. So take a look at that. And again, if you want to extend this to multiple regression, then just put more x's, x2, x3, x4, etc., etc. So yeah, these are another examples. So take a look at this in detail, okay? So those interpretation are important. So you have a p-values. Age is not statistically significant. On the other hand, the education is though, because R, for example, alpha equal 0.01, this p-value is less than 0.01, so very significant. So we reject the null hypothesis that education doesn't affect Y, but we fail to reject for age. So I explain very, very detailed, but I'm just skipping this a lot because it's basically the same thing. So, okay, I think a nonlinear regression, you don't have to know this now, but okay, I think I pretty much explained everything. So, good luck for your project. You know, I honestly think I explained more than what I supposed to do, but good luck for your project. And if you have any question or raise, let me know. And it was actually a pleasure to, teaching with you for this semester. And I hope all the best for you. And then always let me know if you need anything from me. Okay. Thank you so much.